GenAI and MLOps Part 16. This episode has 12 questions. For each question, take a moment to think through your own answer before I share a strong approach. Question 1. MLOps situation. Canary disagreement. Technical metrics look good in Canary, but support tickets increase. How do you investigate and decide rollout? Here's a strong way to approach it. Pause expansion and segment the support tickets by user type, request pattern, geography, model output, and canary or control group. Technical metrics may miss user-facing quality issues, so compare qualitative examples, business outcomes, confidence, and edge cases. If the tickets correlate with the candidate model, roll back or narrow the canary and add a release gate for that failure mode. Nice. Let's continue. Question 2. MLOps situation. Compliance audit. An auditor asks how a prediction made 3 months ago was produced. What evidence should your platform provide? Here's a strong way to approach it. The platform should show the model version, artifact checksum, training data snapshot, feature values or feature snapshot used at inference time, code commit, pipeline run, parameters, approval record, deployment history, input or output logs where legally allowed, and monitoring status at that time. This requires lineage and retention policies designed before the audit, not reconstructed manually afterward. Great. Moving on. Question 3. MLOps situation. Multi-team platform conflict. One team needs fast experimentation while another needs strict approval gates. How would you design the platform for both? Here's a strong way to approach it. Separate experimentation and production paths. Give teams fast self-service sandboxes with quotas, templates, and lightweight governance, while production promotion requires stronger gates, approvals, lineage, security scans, and monitoring. The platform should make the easy path appropriate to the risk level instead of forcing every workflow through the same heavy process. Alright, next question. Question 4. MLOps situation. Stale features. Online feature values are stale but the model endpoint is healthy. How do you detect, mitigate, and redesign? Here's a strong way to approach it. Detect stale features with freshness SLAs, timestamps, missing or update rate checks, and alerts on feature store lag, not just endpoint health. Mitigate by falling back to safe defaults, older champion model, cached validated features, or manual review depending on risk. Redesign with feature ownership, freshness dashboards, backfill or replay jobs, and serving logic that refuses unsafe stale inputs when required. Let's keep going. Question 5. MLOps situation. Disaster recovery. The region hosting your model registry and artifacts is unavailable. How would you continue serving and recover safely? Here's a strong way to approach it. Serving should continue from already loaded model replicas if possible, while new deployments are paused. For recovery, use replicated artifact storage, backup registry metadata, tested restore procedures, and a secondary region with known good model versions. After failover, verify artifact checksums, model versions, traffic routing, and monitoring before resuming normal promotion workflows. On to the next one. Question 6. MLOps situation. Interview unknown. You are asked about an MLOps tool you have not used directly. How do you answer honestly while still showing strong engineering judgment? Here's a strong way to approach it. Be honest about your hands-on level, then map the tool to concepts you do know: orchestration, tracking, registry, serving, monitoring, IAM, scaling, and rollback. Explain how you would evaluate it, what production questions you would ask, and how similar tools behave. A strong answer is not pretending, it is showing that your engineering model transfers across tools. Good. Here's another one. Question 7. Multi-tenant AI platform. How would you design tenant isolation, quota enforcement, and cost attribution for an internal platform that serves LLM access to multiple product teams? Here's a strong way to approach it. Issue each team a scoped API key routed through an internal gateway that enforces per tenant rate limits and token budgets, and tag every request with a tenant identifier so cost and usage can be attributed accurately in billing dashboards. Isolate tenant data, prompts, retrieved context, Log so one team cannot see another's traffic, and give each team visibility into their own quota consumption so they can self-manage before hitting a hard limit. Nice. Let's continue. Question 8. Resume deep dive. Vertex AI pipelines. Walk me through a Vertex AI pipeline you built end-to-end, from training through Vertex AI model registry to production deployment. Here's a strong way to approach it. A typical pipeline starts with a data validation and pre-processing component, feeds into a training component that logs metrics and artifacts to MLflow or Vertex experiments, then a conditional evaluation step that only proceeds to registration if the new model beats the current production model on defined metrics. The approved model is registered in Vertex AI model registry with a version and metadata, then deployed to an endpoint via a canary or staged rollout, with the whole pipeline defined declaratively. Kubeflow Pipelines SDK, so it's reproducible and rerunnable on new data. Great, moving on. Question 9. Resume deep dive. LLM Ops Stack. You deployed Llama 3, Mistral, Allama, and VLLM on Kubernetes. How did you choose between them and scale inference for concurrent users? Here's a strong way to approach it. The choice depends on the use case. Allama is convenient for quick local or dev experimentation and lower throughput internal tools, while VLLM is the production-serving choice for high concurrency workloads because of its continuous batching and paged attention memory management, which dramatically improves throughput per GPU. Model choice. Llama 3 versus Mistral came down to task performance on internal levels versus latency or cost trade-offs at a given size. Scaling concurrent users meant horizontal pod auto-scaling on GPU node pools, request queuing with back pressure so the service degrades gracefully rather than falling over, and continuous batching in VLLM to serve many concurrent requests per GPU efficiently. Alright, next question. Question 10. Resume deep dive. Model monitoring. You used Vertex AI model monitoring and evidently AI for drift detection with automated retraining. How did you avoid false positive retrains? Here's a strong way to approach it. Set drift thresholds based on statistical significance and a minimum sample size rather than reacting to any single alert, and required drift to persist across multiple consecutive monitoring windows before triggering a retrain, so a temporary traffic anomaly wouldn't cause an unnecessary retrain. Retraining was also gated by an evaluation step. The new model only replaced the production model if it demonstrably improved on held-out metrics, so even an unnecessary retrain couldn't silently degrade production. Let's keep going. Question 11. Resume deep dive. Secure MLOps. You implemented IAM, RBAC, Secrets Manager, and binary authorization for AI workloads. Walk me through one specific control and the risk it closed. Here's a strong way to approach it. Binary authorization is a good example. It required every container image deployed to the ML serving cluster to carry a valid attestation from a vulnerability scan and CI pipeline signature before GKE would allow it to run, closing the risk of an unscanned or manually pushed image, potentially with vulnerabilities or unauthorized code, reaching production. This meant no one, including someone with cluster access, could bypass the CI or CD pipeline and deploy an unverified image directly. On to the next one. Question 12. Resume deep dive. GitOps for AI. You used Argo CD and Helm for AI application deployments. How is a GitOps rollout for model serving different from a normal microservice rollout? Here's a strong way to approach it. The Helm chart and Git state track not just application code but the model artifact reference, a versioned URI to the model in a registry or bucket, so a deployment can mean either a code change or a model swap, and both need the same review and rollback discipline. Model serving rollouts also need canary validation against model-specific metrics, accuracy, latency per token, GPU utilization rather than just HTTP error rate, and rollback needs to revert both the serving code and the model version together, since deploying new code against an old model or vice versa can silently break behavior. Good, here's another one. That wraps up this episode. Nice work practicing, and see you in the next one.